Hello, wonderful early college students. Hope you guys are having a good day, and welcome to another week of online learning. This is our sixth week of online learning, and technically, this is the last week that we will actually be going over content and having assignments. So, um, from here on out, uh, yeah, so basically, this is going to be the last week. We have 2 more weeks technically of school, um, but after this week, teachers are not going to be assigning any work. So this will be the last week where I'm giving you guys stuff to do, and then next week it will basically just be a makeup, catch up kind of week. There's not going to be any finals. Normally that week would be finals week, but since we're not having finals, that last week is basically just going to be used to give students a chance to catch up and also to give teachers time to grade any outstanding assignments and to get caught up grading for the end of the semester. So, what we're going to do this week is going to talk about a couple modern physics concepts that I wanted to make sure that you guys at least got a little bit of exposure to in my class before you guys go and possibly see these ideas in other places. So, this week we'll basically be talking about some things that you haven't heard before and that are probably new to you, but are very interesting and things that I wanted to make sure that you got exposure to. Um, and one of those things that I wanted us to talk about is the strong nuclear force. So we spent a good amount of time in this class talking about forces from basically the very beginning of class. And the strong nuclear force is another force I feel like is an important force that I wanted you guys to know a little bit about. So to set the stage for that, I wanted us to consider a helium 4 nucleus. So, helium 4 is just the number of protons and neutrons in the nucleus. So, for helium, that's number 2. Helium is number 2 on the periodic table. That means it has 2 protons. So, if you were going to draw helium, you would basically have you would have 2 protons, and then if it's helium 4, then that means that there's also 2 neutrons in your nucleus. And then your atom has this electron cloud, and those electrons are surrounding the nucleus and they're negatively charged. So this is like a very simple kind of illustration of what a helium 4 nucleus might look like. And we had talked about the electric force, and we had talked about how if you have positive charges, that those charges will be, or if you have the same charge, basically, like charges will repel each other, and opposite charges would attract each other. And that's something really interesting to think about with any nucleus of any atom. It doesn't have to be a helium 4 atom. This is just a simple atom to pick to illustrate the idea. But if you think about any atom, inside the nucleus, you have protons, which are all positively charged, and then you have these neutrons, which are negatively charged. So if you're thinking about that, you're probably looking at this and you're thinking, well, wait, these are protons, and we know that protons are positively charged. And if you remember from our video, we talked about the charge of your proton is about 1.6 times 10 to the negative 19 coulombs. So both of these protons are charged. They have a certain electric charge associated with them, and they're inside the nucleus, which means that they're very close to each other. Um, if you're thinking about the distance between these two particles, that that's an important parameter when you're calculating the electric force between two charges is the distance between them. And if you're talking about inside the nucleus, the distance between the protons in the nucleus is on the order of 10 to the negative 15 meters. So these protons are very, very close to each other and they have a lot of charge. Well, they don't have a lot of charge, but they have some amount of charge associated with them. And so if you know this information, then you know that and if you know that these are positively charged, then you know that these two protons are going to feel some electric force. And you know that if they're positively charged, then those are like charges, and those like charges are going to repel each other. So basically, each of these protons is going to feel an electric force from the other one that's going to want to make these charges repel each other. So there's this electric force between these two charges that would tend to cause these charges to separate. So then you can basically ask the question, why is it that the nucleus of atoms doesn't fall apart? What is keeping the nucleus together? If the nucleus contains protons, these protons are positively charged, they're very close to each other, which means that they would feel the electric force of their neighbors. What's keeping the nucleus together versus breaking apart and going into all these different pieces because all of these protons want to get away from each other? You might think that it has to do with the electrons surrounding the nucleus, keeping things in order, but it doesn't actually have to do with the electrons at all. It has to do with another force that's acting inside of the nucleus, and that force is the strong nuclear force. So basically, when we're talking about the strong nuclear force, um, what we want to think about is that there is a force holding the nucleus together. This force is even stronger than the electric force. And that force is called the strong nuclear force. Right. So just to make clear, we were kind of asking the question, what keeps the nucleus from falling apart? The answer is that there is a force that's holding the nucleus together. It's even stronger than the electric force, and that's what we call the strong nuclear force. And this strong nuclear force is basically is a force that is due to it's a force due to protons and neutrons being very close to each other. And when I say being close to each other, we're thinking about around these characteristic length scales. Around the scale of like 10 to the negative 15 meters, that's when the strong nuclear force is going to take hold. The strong Once you're outside of like the nucleus, the strong nuclear force becomes very, very insignificant. It's only present when the particles between particles in the nucleus when they're very, very close to each other. So that's basically the strong nuclear force, and it's the force that's responsible for holding the nucleus together. It holds the nucleus together. So you could basically, to get an idea about how strong this force is, we can use what we know about the electric force to figure out what's the magnitude of this electric force based on these protons being at this distance. And that's something that we can do just from our knowledge of Coulomb's law. Um, if we remember, we talked about Coulomb's law at the very beginning when we started online learning. And that the equation for Coulomb's law, which was the formula for the electric force, it looked like this. It was a constant times the two charges that are involved divided by the distance between them squared. It was a formula that looked very much like gravity, in that it was a constant times the product of the two charges instead of the two masses, because it's relating to electric charge, the force of an electric charge versus the force due to mass, which is gravity. And then it was still divided by the distance between them. And we have all of that information, including the value for k. The value for k, if you remember from that class, was 9 times 10 to the 9. Then we've got those two charges, and each charge has a value of 1.6 times 10 to the negative 19. So there's two of those protons which have the same charge. So both of those charges are going to have the same numerical value. And then the distance between them was 10 to the negative 15. And that distance is squared in my formula, so I have to remember to square it here as well. And if I plug all of that into my calculator, that's how I would find my answer. And if you plug that into your calculator, or if you plug it into Desmos, you should get an answer that is around 230.4, and that answer is going to come out in SI units of newtons. So those protons, the two protons that are inside that helium nucleus, these two protons are repelling each other with about 230 newtons of force, which is, if you're thinking about a different kind of frame of reference, that's about 51 pounds of force. So a fairly significant amount of force, especially when you consider how small these individual protons actually are. So the electric force is very large when these protons are very close to each other. The strong nuclear force has to be even stronger than that, right? If the electric force is repelling, then the strong nuclear force has to be keeping everything together. It's kind of almost like a gravitational force that's keeping these things together, and it has to be much stronger than this. If the electric force is 230 causing everything to separate, then there has to be a strong nuclear force that's causing everything to be compressed together with a force greater than the electric force. Otherwise, the nucleus would fall apart. And if you wanted to if you wanted to take apart a nucleus, if you wanted to take the individual protons and neutrons out of the nucleus, then you have to overcome these forces. And you would have to be overcoming those forces over a certain amount of distance where those forces are acting. In other words, you would have to do work. So there's energy contained within the nucleus just based on the fact that these particles are so close to each other, and it would require energy for you to take them apart. So that gives all matter a form of stored energy, and that's kind of related to Einstein's E equals mc squared. There's a strong connection there between the nuclear force. There's a connection between the strong nuclear force and Einstein's equation. And if you take more physics classes, you'll learn a lot more about that. Um, that that's something that I wanted to talk more about, and so I'm glad that I got at least a little bit of chance to do that here. And yeah, I hope you guys are doing well. I hope you guys are finding this information interesting, at least to some extent, learning some things that you didn't know. So yeah, if you guys have any questions, feel free to reach out. And if not, then I will see you in the next video. Thank you for your time and have a good day.